In this video lecture, first we'll define the statement of Stokes theorem, and then we'll understand how it works and how we can evaluate it via a numerical example. So let us begin with the formal statement of Stokes theorem. Let we have a vector field F which has components F1, F2 and F3. In general, these F1, F2 and F3, they are the functions of X, Y and Z. And what we need here, the first order partial derivatives of F1, F2 and F3 with respect to X, Y and Z. They must be continuous. And in addition to the continuity of the individual components of the vector field, we needed an oriented, piecewise smooth surface which is bounded by a closed curve C. Before we write the expression for the Stokes theorem, first let us understand the nature of surface we require, which will be applicable in the Stokes theorem. So let us take an example. Suppose this is our three-dimensional coordinate system. This is say x-axis, this is y-axis and this is z-axis. We have a surface like this, which is in general in space, and what we needed for this surface has to be piecewise smooth. So this shaded region is actually the part of the surface. So this is what we are calling as capital S, and this surface is bounded by a simple closed curve C. This surface is bounded by a simple closed curve C. If all these things are happening, then we have a result which says the line integral f dot dr around the closed curve C in the counterclockwise direction. This is going to be the direction of the line integral. This is equal to the double integral of curl of f dot n cap d rho over the surface S. Here n cap is the unit outward normal to the surface S. And del cross f, obviously it's a curl. So this Stokes theorem actually relates the line integral f dot dr around a simple closed curve C, which is equal to the surface integral of the normal component of del cross f. This is equal to minus y square I plus xj plus z square k. This is the given vector field, and S is the surface which is intersection of the plane y plus z equals to 2 with the right circular cylinder x square plus y square equals to 1. So we wanted to verify the given vector field for this surface, that is, we wanted to check f dot dr equals to double integral del cross f dot n cap ds. Sorry, this is d rho. and this is about the surface S. So let's first draw the surface S. So we have this situation. This one is suppose x-axis, this is y-axis, and this is z-axis. And we have a plane y plus z equals to 2. So say this is going so here this shaded region is the intersection of y plus z equals to 2 y plus z equals to 2 with the cylinder x square plus y square equals to 1. So here our surface S is piecewise smooth oriented and it is bounded by a simple closed curve, which is this one. This is our C. Now let's try to verify the given Stokes theorem statement by evaluating both the ends of this expression. So let us start with the left hand side, and we wanted to evaluate CF dot dr. To solve this integral, first we need to identify the closed curve C. Means we are looking the equation of this curve C. So in general, we know any curve in a space, we can write its vector equation R equals to xi plus yj plus zk. Since in the base we have the equation x square plus y square equals to 1, so the parametric equation will be x equals to cos t, y equals to sin t, and t ranging between 0 to 2 pi. And we know from y plus z equals to 2, z equals to 2 minus y, which is equals to z equals to 2 minus sin t. So from here we got the values of x, y and z. So we can put these equations here and we'll get the equation of our curve C, which is R equals to cos ti plus sin tj plus 2 minus sin t k. And now we can convert this integral over CF dot dr as integral f dot dr by dt, where t ranging from 0 to t equals to 2 pi. So let's first evaluate the value of dr by dt, and then we'll evaluate f dot dr by dt, and then we'll put here in this integral. So dr by dt is going to be dr by dt, this is going to be minus sine t plus cos tj minus cos tk, and we know the value of f, it is minus y square I xj plus z square k. So f will have the value in parametric form. F equals to minus y square t means sine square ti plus cos tj minus cos tk plus 2 minus sine t k. Because we had the value of f as minus y square plus xj plus z square k, so we have inserted the values of x, y and z in the vector field f, and we got the same vector field in parametric form. So f dot dr by dt, this is going to be sine cube t plus cos square t minus 4 plus sine square t minus 4 sine t. So this is the value of f dot dr by dt, which we can simplify, and we can have its value as sine cube t plus cos square minus 4 here we have cos t as well in the multiplication, minus 4 cos t minus sine square t cos t plus 4 sine t cos t. Let's put the value of f dot dr by dt in this integral. So we are going to have this value integral f dot dr by dt 0 to 2 pi, this is equal to integral sine cube t 0 to 2 pi sine cube t plus cos square t minus 4 cos t minus sine square t cos t plus 4 sin t cos t dt. So once you solve this integral, this value will be 0, cos square t will be pi, and minus 4 cos t will be 0, sin square t cos t will be 0, and 4 sin t cos t will be 0. So its value will come out pi. So this is the left hand side of this integral. Now let's try and evaluate the right hand side of the integral RHS, which is double integral del cross f dot n cap d rho over the surface S. Here we should also note down, many times we write the same integral like this: double integral over the surface S del cross f dot d rho, and this time this d rho will behave like a vector. So it has these two kind of representations. So now first evaluate del cross f. So del cross f, this is going to be I, j, k. Let's put the values of x, y and z here. So del x, del y, del z, and minus y square x and z square. So once we solve it, we are going to get 1 plus 2y times k. So this is the value of the curl of f. Now let's see our picture again, which we have drawn for this case. So since we are evaluating here a surface integral, so we need to take the projection of this surface S in any one of the plane. So here our natural choice is xy plane. So if you take the projection of this surface S into xy plane, so its projection is going to be a circle in xy plane whose radius will be 1. So our P is going to be k cap in this particular case. So let's put everything here in the integral. So this double integral del cross f, which just now we have evaluated its value, dot n cap d rho over the surface S, we can write like this: double integral del cross f dot n cap, and now we'll write the equation of the surface is y plus z minus 2. This is g. So it is going to be mod del g divided by mod del g dot k cap. K cap because we are going to take the projection in xy plane. Here we can write dx dy. So now let's evaluate everything one by one. Let us begin with the surface G, which is y plus z minus 2. Let's evaluate its gradient, del G, which is equals to j plus k. The absolute value of del G will be equal to under root 2. Mod del G dot k is going to be 1. Now we are ready to put everything in the integral except the n cap. So let's just evaluate the value of n cap, which is unit outward normal to the surface. It is going to be del G divided by mod del G, which is equal to j plus k divided by under root 2. Now we'll put each and everything in this integral to have the value of this integral. So double integral, the value of del cross f 1 plus 2y k dot n cap, which has the value j plus k divided by under root 2, now the value of mod del g, which is under root 2, and del g dot k, which has the value 1. Since we have taken the projection in xy plane, so dx dy, and the region is the unit disk, x square plus y square less than or equal to 1. So now let's simplify this integral over the region R. 1 plus 2y, this under root 2 will cancel out under root 2, dx dy. For the ease of doing this integral, let's convert everything into polar coordinates. 1 plus 2r sine theta r dr d theta r equals to 0 to 1 and theta from 0 to 2 pi. Let's solve this integral first for r. Theta 0 to 2 pi, and once we'll integrate, it will come out r square by 2 plus 2r cube by 3 sine theta, limits of r 0 to 1 d theta. After substituting the value of r, it is going to be 1 by 2 plus 2 by 3 sine theta d theta. Now once we'll integrate, we are going to get the value as 1 by 2 into 2 pi, and the value of the integral sine theta between 0 to 2 pi is going to be 0. So the final value for this integral is 0. So in this case, we verify that the circulation, which is the line integral f dot dr, this is equal to the normal component of del cross f and its surface integral over the surface S.